Let's do an interesting integral. Let's say we have the integral of 1 over x squared dx from 1 to infinity. So first of all, let's think about what this means, and then let's try to actually evaluate it. So let's first graph 1 over x squared. So we only care about this graph from 1 to infinity, right? I mean, we can't graph it to infinity, but we can see how it behaves. So we know that from 0 to 1 it behaves really weird, right? It goes to like infinity, but at 1 the value of it is actually at 1, right? The y value, y coordinate of it is 1. Now, as it goes to infinity, it approaches 0, right? So it looks something like this. So there's a horizontal asymptote at 0. And our goal here is to find the area, right? Because integral, the area from 1 to infinity. So 1 to infinity. But if you notice that as it approaches 0, the area is just going to get very, very close to 0. So the only parts that will make a significant difference in the area is the beginning parts, like 1 to 5, right? Like 1 to 10. And then afterwards, it's just going to get very, very small areas, which will make a huge difference. Now let's talk about how we can do this mathematically. So this right here is called an improper integral. For an improper integral, we need to use limits and integrals. We need to rewrite this integral as the limit. So I'm going to choose a variable. It doesn't matter what variable we choose. I'll choose b, right? Because the bounds are usually a to b. So I'll say the limit as b goes to infinity of the integral 1 to b of 1 over x squared dx. And the reason why I do this is because we need to use a limit to do this. We can't really have a bound that's infinite, right? So let's now evaluate this limit, or sorry, this integral like we usually do. So I'm going to rewrite this as, so I'm going to keep writing the limit because I want to make a point here. So we have the limit as b goes to infinity of the integral 1 to b of x to the negative 2, right? Because we want to evaluate this integral, I'm going to write it as a power, x to the negative 2 dx. Now here we can simply use the anti-power rule. We can add 1 to the power and divide by the power. So this becomes the limit as b goes to infinity of the integral 1 to b. Actually, we're going to do the integral now, so I'm not going to write the integral anymore. So x to the negative 1, right? We're adding the 1 to the power, and we're dividing by the power. So this is dividing by negative 1, so this just becomes negative. And remember, this is from 1 to b. Okay, so let's evaluate this. So we have the limit as b goes to infinity still of negative x to the negative 1 minus negative 1 to the negative 1, which is just negative 1, right? Okay, so this, it seems like now we can substitute b in here, so let me rewrite this. Actually, we should have done it in the previous step, but we'll do it right here. So the limit as b goes to infinity of negative b to the negative 1 plus 1, right? Because negative and then a negative right here. Okay, so now this is just a regular limit problem, right? After we evaluate the integral at the bounds, we just treat this as a regular limit problem. So as b goes to infinity, let's think about what happens. So I'm going to rewrite this actually. The limit as b goes to infinity of, well, negative b to negative 1 is just negative 1 over b, right? Because we have x to the negative a is equal to 1 over x to the a. So this is negative 1 over b plus 1. Now, think about what happens if b goes to infinity. So maybe pause the video here. Think about what happens as b goes to infinity. Okay, so I'm going to move up here. So if b goes to infinity, well, that term just goes to 0, right? So then this is just equal to, so the limit as b goes to infinity of negative 1 over b plus 1, well, that's just equal to 1. So the area under this curve from 1 to infinity is just 1. And that right there is an improper integral.